So in the last lecture, we started with image degradation. We have seen what is degradation model. Now today we'll see what is noise model. So it is possible to represent random noise as a mathematical function, and that is exactly what a model is. The distribution of the noise is based on probability. Hence, the model is called a probability density function, PDF. Once noise has been quantified, creating filter to get rid of becomes a lot easier. So what is probability density function? Consider the distribution of numbers as shown in the figure here. The vertical axis represents probability and the horizontal axis represents numbers. The probability a randomly picked number, say x, lies in the range from a to b is equal to the area of the curve between a and b. Now here, if you pick a number randomly, then there is a 0% chance that it will be a number 49. That is because the area between 49 and 49 is 0, right? Similarly, there is a 75% chance that the number will be minus 73 or 49. That is because a lot of area under the curve is between minus 73 and 49. There is a 100% chance of picking a number between plus infinity or minus infinity. Now we'll see what is mean and variance. The mean is roughly the middle value of the entire distribution, and the variance is a measure of how much the probabilities vary. A greater variance means you are more likely to get several different values, and a smaller variance means you will get lesser different values. So in this figure here, the one on the left hand side is broader. So you will end up getting lots of minus 73s and 49s. But the one on the right hand side isn't. So you won't end up with lots of minus 73s and 49s. Let us now discuss the different types of noise that we can have in an image or a video. So here I have shown Gaussian, Rayleigh, Gamma, Exponential, Uniform and Impulse noise. We have already discussed what is Gaussian and salt and pepper noise while studying filters. So let us just start with Gaussian noise. The PDF, that is probability density function for Gaussian distribution, is given here. P of z equal to 1 upon square root of 2 pi sigma e raised to minus z minus mu the whole square upon 2 sigma square. Here sigma is the standard deviation of the noise and mu is the mean. So Gaussian is an additive noise. It affects every pixels in the image. It affects every pixel in the image. It is mostly used as a noise model in most image and video processing systems. It is mathematically very easy to work with, and it is a good approximation for other types of noise. If the curves here represent noise, then what would it mean? Let's consider the blue PDF. The mean value of the noise will be minus 2. So, on an average, 2 would be subtracted from all pixels of the image. You will also have 7 being subtracted or even 3 being added as noise. This is because the distribution extends of a broad range of values. In the red PDF, the mean value is 3, so on an average 3 would be added to all pixels, some pixels having 1 added or 5 added. But because the distribution isn't that wide, you will see a narrow variation in noise. In the image here on the left hand side, it's the original image. Okay, you can see the histogram of the original image. Here there are only two levels of histogram. One is for black, another is for the gray. When Gaussian noise is added to this original image, on the right hand side you can notice, see the histogram of the noisy image. The histogram looks like a Gaussian curve, right? So you can easily say that the image is affected because of Gaussian noise. Okay, once you notice that the image is affected with Gaussian noise, you can use a particular filter to remove that particular noise. So generally Gaussian noise occurs in an image due to noise in electronic circuits and noise in the sensor itself, may be due to poor illumination or at times even high temperature. Unlike the Gaussian distribution, the Rayleigh distribution is not symmetric. It is given by the formula P of z equal to 2 upon b into z minus a into exponential e raised to minus z minus a the whole square upon b for z greater than or equal to a and 0 for z less than a. It models as a real sensor noise. It appears in real physical system and appears in magnetic resonance imaging. It is interesting to note that the Rayleigh distribution is skewed to the right. Next, we will see what is gamma noise. The shape of the gamma noise is very similar to the Rayleigh distribution. The gamma noise distribution starts from 0 and it is given by the formula which is shown here, Pz equal to a raised to b z raised to b minus 1 upon b minus 1 factorial e raised to minus sz for z greater than or equal to 0 and 0 for z less than 0. Here less than a is less than 0 and b is a positive integer. Okay, and the mean and variance of the distributions are given by mu equal to b upon a and sigma square is equal to b upon a square. Next is exponential noise. Exponential distribution has an exponential shape. It is given by the equation P of z equal to a into e raised to minus az for z greater than or equal to 0 or 0 for z less than 0. Here a is greater than 0. The mean and the variance of the exponential noise is given by mu equal to 1 upon a and sigma square equal to 1 upon a square. It doesn't have negative values. The prediction error is normally modeled using this noise. Now this prediction error we have studied in LPC, lossless predictive coding in compression. Now we will see what uniform noise is. As the name suggests, the noise is uniform over a certain band of gray levels. The PDF of uniform noise is shown here in the figure. So it is given by P of z equal to 1 upon b minus a if z is greater than or equal to a and less than or equal to b and 0 otherwise. The mean of the function is mu equal to a plus b upon 2 and the variance of this function is given by sigma square equal to b minus a the whole square upon 12. Okay, so quantization noise which we have studied during sampling. Okay, so sampling and quantization. So quantization noise can be modeled using this noise. So inside the interval noise exists and outside it is 0. Both uniform and exponential models are useful on the operations which are performed on image and video. Next is salt and pepper noise, which we have already studied. During image enhancement techniques. It is also known as impulse or random noise. The PDF of this noise is given by the formula P of z equal to PA for z equal to A, PB if z equal to B and 0 otherwise. In this, with one probability we change the pixel to white, that is salt, and other probability change the pixel to black, that is pepper. Salt and pepper will affect some pixels more or some not. But when it affects, it will affect all of them in the same fashion. Example, in camera sensor, one pixel is not giving any signal, that is pepper noise, and it is shown by black. So histograms can be used to identify what kind of noise is present in the image. Here you can see for the first image, the shape of the histogram is similar to the PDF of exponential noise. So we can say that exponential noise is present in the image. Similarly, we can identify that the second image is degraded by uniform, and third image by salt and pepper noise. So after identifying the noise, it is very easy to apply the filter to remove the noise. These are the examples for Gaussian, Rayleigh and gamma noise. We can have combination of noise also. Example, Gaussian may be in the circle, okay, here the circle may be affected by the Gaussian noise, then maybe the outside the circle, that is the rectangle, may be affected by the uniform noise, and so on. So now we'll see what is the difference between image enhancement and image restoration. The first point, as the name suggests, in image enhancement, the original image is processed so that the resultant image is more suitable than the original for specific applications. Under restoration, the first point is the aim of image restoration is to bring the image towards what it would have been if it had been recorded without degradation. Second point, under image enhancement, the image enhancement makes a picture look better without regard to how it really truly should look. Second point, under restoration, image restoration tries to fix the image to get back to the real true image. The next point under image enhancement means improving the image to show some hidden details. Restoration, third point, image restoration means improving the image to match the original image. Fourth point, under enhancement, image enhancement is a purely subjective process, okay, but restoration is an objective process. Now what is subjective process? The user decides the quality of the image or the result of the image, and objective means the mathematical formulas are used in restoration. The last point, that is fifth point under enhancement, image enhancement is a cosmetic procedure, that is, it does not add any extra information to the original image. It merely improves the subjective quality of the images by working with the existing data. And in the restoration, it tries to reconstruct by using a priori knowledge of the degradation phenomena. The restoration hence deals with getting an optimal estimate of the desired result.